Hello, my name is Robert, and today I'm going to tell you about experimental advantage in learning with noisy quantum memory. This is a joint work with Michael Broughton, Jordan Cutler, Sitan Chen, Jerry Lee, Richard Kuhn, John Praskell, and Jerry McLean. One of the central goals of many scientific disciplines is to learn how the physical world operates. Throughout history, people have built several various measurement apparatus, like telescope and microscope, to understand various aspects of the universe. For example, people can utilize telescope to understand astronomical objects like other planets or even black holes, and utilize microscope to understand and to learn about small microscopic objects like viruses and atoms. Essentially, this measurement apparatus enables us to better learn about how the physical world operates and make prediction of our universe. In this talk, I will consider learning as a combination of receiving information from nature, processing the information, and storing the information in some memory storage, such that subsequently we can make prediction based on the stored information. In the conventional experiments that scientists currently do in the lab, we receive information from the system of interest. For example, if people have constructed some exotic material, people wanted to learn about this material by performing physical measurement to obtain classical information. We can then process this classical information through classical computation or storing them in classical memory. As quantum technology starts to emerge, one could begin to imagine what a futuristic experiment enhanced by quantum technology could look like. Instead of receiving classical information by performing measurement, one could utilize powerful quantum sensors to transduce quantum information from the actual physical system to our quantum computing system. We can then process these quantum information through quantum computation and store them in quantum memory so that we can then combine with future quantum information to make prediction about the physical system. A natural question that one might ask is, what are the advantages of quantum-enhanced experiments over conventional ones? And more broadly, how could quantum technology fundamentally alter our ability to learn about the physical world? In this talk, I will provide some concrete answer to these questions. So the talk will be outlined as follows. I will first discuss the theory for learning physical system and what kind of advantage a quantum-enhanced experiment could have. I would then briefly discuss the situation for learning physical dynamics. And finally, we will provide experimental demonstration of these advantages on the Sycamore processor. So let's first begin with the first part on learning physical system. Here we will assume that we have an unknown physical system represented by a density matrix rho. So if you assume quantum mechanics, then any physical system can be represented by a density matrix. We assume that there is a physical source that could generate a single copy of this physical system at a time. So for example, you might need to go through some synthesis process or certain kinds of cooling process or certain kinds of state preparation process to prepare such a physical system rho. And then we would like to utilize conventional experiments or quantum-enhanced experiments to learn about this physical system rho. Such a framework has also been considered in the following paper. In particular, in this earlier talk by Dorit, she had proposed a framework that is closely related to the one that I'm going to discuss. The framework that I'm going to talk about would seem much simpler than the framework considered in Dorit's talk, this QUAM framework. However, using mathematical reduction, one could show that these are actually equivalent frameworks. So let's begin with conventional experiments. So here, we consider that some physical source generate a single copy of rho, where the scientists would then perform some POV measurement to obtain some classical data about this physical system. We would then store this classical data in a classical memory, and then we can process this classical data to select the next experiment that we would like to perform. We can then perform the next POVM experiment, obtain the classical data, process them, and then select for the next one, and so on. So this process could repeat for multiple rounds. And finally, at the end, you will have this chunk of classical memory that stores all the data from all the POVM measurement. And after that, we would process all of these classical data to make prediction about this physical system rho. Quantum enhanced experiments share some similarity with conventional experiments, but also have some major differences. Instead of performing measurement on the physical system to obtain classical data, we would utilize quantum sensor to transduce this quantum state into our quantum computing system. We would then store this quantum information that we obtain from quantum sensors in a quantum memory. But then in the next step, since we're just getting the entire information from the physical system, we don't have to choose what kind of measurement we wanted to perform next. What we would do is we would use the same quantum sensor again to transduce this quantum information into our quantum computing system, which will then be stored in quantum memory again. We would repeat this process for many rounds. And at the end, you will have this big chunk of quantum memory that stores all copies of this unknown physical system rho, which we will then process these quantum data through quantum computation to make prediction about this physical system. So here's a side-by-side comparison between conventional experiments and quantum-enhanced experiments. One of the major differences between the two is that in quantum-enhanced experiments, we have this availability of quantum memory that allows us to store quantum information from all past experiments, so that at the end, we can entangle quantum information from both past and future experiments to extract information. So from a mathematical perspective, you can also refer to all the protocols in conventional experiments as algorithm without quantum memory, because there's no quantum memory, there's only classical memory. You cannot entangle quantum information from past and future experiments. And all protocols in quantum enhanced experiments as algorithms that could utilize quantum memory. So now, after defining this mathematical framework for talking about conventional and quantum enhanced experiments, we can start proving theorems about what kind of advantage could one have using quantum enhanced experiments versus conventional experiments. So the first example that I would show is predicting incompatible observables. So recall that in quantum mechanics, there's this notion of incompatibility between different properties. The most famous example is position and momentum. If you wanted to measure position accurately, then you couldn't measure momentum accurately, and vice versa. However, basically you can rigorously prove it, but that actually only holds when you consider conventional experiment. That is, you have a single copy of the unknown physical system that you wanted to measure. However, if you consider a quantum enhanced experiment where you could have a quantum memory that stores quantum information from all the different rounds of experiments and then perform a joint quantum processing of it, then you can actually circumvent these kind of incompatibility to a certain degree. More precisely, we consider the task where we have an unknown quantum system rho, where the algorithm tried to learn this quantum system through the framework defined before, such that after learning, we will ask the algorithm to predict some observables from a collection of exponentially many incompatible properties. And the goal is to utilize the smallest number of copies or experiments or the smallest number of queries to this physical source. In particular, in this following works, starting from my paper with Richard Kuhn and John Praskol, and follow up with this theory paper with Sitan Chen, Jordan Kotler, and Jerry Lee, we showed that if you wanted to predict incompatible observables in an unknown physical system, then learning algorithm with quantum memory would only require a polynomial number of samples, but all learning algorithm without quantum memory would require an exponential number of samples. Here is a concrete example of this fact. Suppose that you have an n-qubit state rho that's given by I plus p over 2 to the n, where you don't know what this observable p is. So if you look closely at the state, it's actually a classical probability mixture over product state. So there's no entanglement in such a physical system. There's only classical correlation. And then the goal is that after learning this unentangled physical system, we would like to predict the expectation value for some observable Q. Even for this unentangled state, one could prove that there is an exponential separation between learning algorithm with quantum memory and those without quantum memory. Hence, establishing an exponential separation between quantum enhanced experiments and conventional experiments. So interesting thing to note is that if you just have a physical system that have no correlation between the different constituents, which is also known as a product state, then there cannot be a large quantum advantage because the conventional experiments could learn such a state very efficiently by performing single qubit tomography. However, if you add on top of it some classical correlation, that is, you consider a classical probability distribution over these product states, then suddenly exponential quantum advantage emerges. So that is one example of exponential advantage. Another important example for exponential quantum advantage of utilizing a quantum-enhanced experiment is performing quantum principal component analysis. The setup is similar. You have some unknown physical system rho, and the algorithm would like to learn about this rho, such that after learning, what the algorithm has to do is it has to be able to estimate a property for the principal component of this physical system rho. In this work, we've proved that in order to estimate properties of this principal component in an unknown physical system, we can, similar to before, we can show an exponential advantage of utilizing algorithms that have quantum memory. So now that concludes the discussion for the first part of the talk. For the second part of the talk, I will provide a brief discussion for the situation in learning physical dynamics. It's very similar to learning physical systems, so I would keep it brief. Here, instead of learning about a physical system represented by a density matrix rho, we wanted to learn about an unknown physical dynamics. For example, some chemical process that happen in nature or the photosynthesis process. Maybe we want to learn about some properties or structure of the physical dynamics so that we can know why they are so efficient and how we can improve them and so on. In quantum mechanics, any physical dynamics can be represented by a quantum process, also known as a quantum channel. Here, each experiment will consist of a state preparation, so you prepare some initial state, evolve it under this physical dynamics, and for conventional experiments, we will perform a measurement to obtain classical data. But for quantum-enhanced experiments, we will utilize quantum sensor to directly obtain the output state from the output system from after the evolution. Such a framework has been considered in my previous paper in Richard Kuhn and John Praskal, as well as this independent work by Aharonov, Kotler, and G. Similar to learning physical systems, we can also prove that for several tasks, there is an exponential quantum advantage. So for example, if you wanted to learn and approximate models of some polynomial time quantum processes, we can show that learning algorithms with quantum memory only require a polynomial number of experiments, but all learning algorithms without quantum memory would require exponentially many experiments. Another example is uncovering whether a scrambling dynamic is time reversal symmetric. We can show that a learning algorithm with quantum memory would only require a constant number of experiments, but all learning algorithms without quantum memory require exponentially many experiments. So such a theorem was initially studied by Aharonov, Kotler, and Chi, where they proved that this exponential advantage when we restrict to a special class of algorithms without quantum memory. However, in the follow-up work, we proved that the theorem actually holds for the general class of all possible algorithms without quantum memory. So that concludes the discussion on the theoretical aspects of this talk. So recall that in the previous discussion, we have assumed that the operation, like the sensors and the quantum computation and the memory, they're all perfect. There's no noise in all of them, in any of them. But in practice, especially in our NISQ era, there's going to be errors that happens everywhere. There's going to be noise in your memory. There's going to be noise in the operation you do, and so on. So we would like to understand whether such a significant exponential advantage could still be evident utilizing a NISQ quantum device. So that would be the major focus of the third part of this talk. The first experiment that we consider is this task of predicting highly incompatible properties. Here we have an unknown quantum system rho, which we will then, where the algorithm will learn through experiments. And after learning, we will ask the algorithm to predict some properties. This physical system that we will consider is this unentangled state that I previously mentioned before. So there's no entanglement in this physical system, and the preparation is very easy. All we have to do is start from the all-zero state, apply some bit flip according to some classical probability distribution, and rotate them to the right basis. So now we wanted to utilize conventional experiments or quantum-enhanced experiments to learn about this physical system. For conventional experiments, we will utilize the classical shadow formalism based on randomized Pauli measurement to predict properties of this physical system. And for quantum-enhanced experiments, we would consider the availability of this external quantum memory that allows us to store one additional copy of the system role from a previous experiment. We will now perform an entangling operation between the two copies, followed by a computational basis measurement. Both conventional experiments and the quantum-enhanced experiments will be repeated multiple times to gather the data. So now, after gathering a collection of data, we will predict the properties of the physical system utilizing the collected data. We implement this utilizing a 40 qubit subset of the Sycamore processor, where the blue qubits will represent the system, like the state role, where the red qubits will be the memory qubits that stores this additional copy of row. So note that this is probably the structure have been seen from the previous talks already, where this blue adjustable couplers allows us to implement some entangling gates. In particular, we will consider the classification task. That is, we will ask the algorithm to predict if one Pauli observable has a larger magnitude than the other Pauli observable for the unknown physical system. Results are shown in this plot. The green axis are the number of experiments for running conventional experiments to achieve a prediction accuracy of greater than or equal to 70%. We also show this dashed line, which is a rigorous fundamental lower bound that you can prove from the framework that holds for any conventional experiments. Furthermore, this dashed line holds in the sense that you don't have any error in your measurement parameters and the operation you could do and so on in a perfect conventional experiments. Essentially, this this dashed line tells us that for any conventional experiments, the number of experiments required would always be above this dashed line. However, this doesn't hold for quantum-enhanced experiments. And as you can see, if you utilize the quantum-enhanced experiments, you can achieve an accuracy of 70% or 80% with a much fewer number of experiments. In particular, when you look at a system size of 20 qubits, you can see that using quantum, you only need roughly 100 quantum-enhanced experiments, but you actually require nearly 1 million conventional experiments, which will take significantly longer time to achieve. And furthermore, this could be much more significant than computational speed up, because in practice, maybe one generation of just one physical system role may already take a few seconds or 2 minutes or even hours. If that is the case, then the speed up would be very, very significant. In the next experiment, we will consider the task of uncovering time reversal symmetry. Here we will be given some unknown quantum dynamics U. The algorithm will learn this dynamics U through experiments, such that after learning, the algorithm can predict whether this U is time reversal symmetric or not. Here we will consider this unknown dynamics as some quantum supremacy type circuit. So we generate this dynamic by composing single qubit rotation followed by the Sycamore gate. In a conventional experiments, we would start from the all-zero state, evolve it through this evolution, and measure in the Y basis. The reason that we measure in the Y basis is that as long as the dynamics satisfy time reversal symmetry, one could prove that the expectation values of all of these Pauli Y operator will be 0. On the other hand, if the time reversal symmetric does not hold, then with probability 1, these Pauli Y operators will be non-zero. So by checking the expectation value, you can distinguish between time reversal symmetry versus non-time reversal symmetry. On the other hand, the quantum enhanced experiments would be much more complicated. In particular, we will utilize this external quantum memory that spans across two different experiments, essentially two different evolutions of this unitary U. We start from an initial state that entangles between the system qubits and the memory qubits, evolve under this evolution U, while keeping the memory coherent. So what we're going to do there is to perform some kind of the spin echoes, or also known as dynamical decoupling, to keep the memory storage as coherent as possible. We will then follow by an intermediate unitary, and then run the next set of evolution. Finally, we will perform an entangling circuit between the system qubits and the memory qubits, and followed by a computational basis measurement. Similar to before, we will run both experiments for multiple times and utilize the collection of data to predict whether the dynamics satisfy time reversal symmetry or not. Again, we are going to utilize this 40 qubit subset from the Sycamore processor. The blue qubits will be the system qubits, and the red qubits would be the additional external quantum memory. We would then apply this one-dimensional supremacy type scrambling on the blue qubits. More precisely, what we're going to do is we will consider different type of different random dynamics, random unitary, and we would gather data for each of the random unitary. And now we would just hand this entire collection of different dynamics to an unsupervised machine learning model. What the machine learning model would do is, given this experimental data, it would try to discover the underlying symmetry pattern. More precisely, in the following two plots, every point in the two-dimensional plot represents a different dynamics. So for example, in the left-hand side figure, what we do is we take data from conventional experiments for all of these different dynamics, and we feed it into an unsupervised machine learning model who will try to discover a two-dimensional representation that maps out the pattern that it found. And as you can see, in the left-hand side figure, dynamics that satisfy time reversal symmetry and not are all being mixed together. Basically, the machine learning model didn't discover any particular pattern. From figure to the right, when you train the same unsupervised machine learning model, but with data from a quantum enhanced experiment, we can clearly see that the machine learning model discovered the underlying symmetry pattern in that it's placing all the dynamics that have time reversal symmetry to the right and those that are general to the left. We can then ask the unsupervised machine learning model to perform a clustering, that is, use clustering technique to cluster all these different dynamics into two classes. We can then test if the clustering, the two classes found by the unsupervised machine learning model, matches with the two classes, that is, whether it's a general evolution or a time reversal symmetric evolution. The results is shown in the figure here, where on the left-hand side, we provide the prediction accuracy, so the higher the better, for data from physical experiments, and to the right, we provide the prediction accuracy for data from a noiseless simulation. So recall that in physical experiments, there will be noise everywhere, like there will be noise in your memory storage, there will be noise in the operation, and so on. On the right-hand side, you can see that quantum enhanced experiments perform really well. And for conventional experiments, as system size grows, the number of required measurements, the number of required experiments scales exponentially in system size to achieve a fixed amount of accuracy. And furthermore, in the physical experiments, you can see that despite all the noise in the systems and the memory and so on, quantum enhanced experiments still achieved a very good accuracy. On the other hand, conventional experiments actually fails pretty miserably. There's actually an explanation for that. The reason is that conventional experiments require distinguishing between two exponentially close numbers. And when there are noise in the systems, that noise would just overwhelm the signal, and then the conventional experiments would fail miserably. On the other hand, we can see that quantum enhanced experiments not only doesn't scale exponentially in system size, but it's also much, much more robust to noise in the system. So to conclude this talk, we showed that our ability to learn about the physical world can be exponentially improved using quantum technology. That is a combination of quantum sensor, quantum memory, and quantum computer. Furthermore, the demonstration on the Sycamore processor shows that the significant advantage in learning ability could already be evident using a noisy intermediate scale quantum technology. Hence, this shows that we are hopeful that in the coming years, it's possible to utilize NISQ quantum technology to enhance and impact different scientific disciplines. That's it for my talk. Thank you so much for listening.